Hello, I'm Dave Thibodeau. Today we're going to talk about number formats, and specifically fixed point number formats, how it's shown in binary, and uh, and how real numbers get realized in a fixed point system. Now, please bear with me on this. This is a topic that a lot of people have trouble with and seems very confusing. I know that you can understand this. So my teaching style is a little bit different. Bear with me. Stick with this for a little while, and I'll show you how easy it really is. Anyways, okay, I went ahead and counted out um, a 5-bit binary number. We're going to start simple. I'm not going to start with a great big number, 24-bit number or anything like that. We're just going to start with a 5-bit number. We're going to do a 1.4 format. So it's 5 bits, 1.4. What that means is when you put a number, whenever we're going to put a number like, uh, uh, 1.675 as a real number, the 1 is a whole number portion, and the 0.675 is a fractional portion. Um, and obviously, we can show it as a fraction, or we can show it as a decimal representation of a fraction. So, where's my wiper here? So, we're just going to keep it simple with a 5-bit number. So, it'll be a 1.4 format, with one bit being a whole number bit and then the other 4 bits as the fractional part. So obviously, we're only going to be able to get to a 1 uh, for the whole number because it's binary, it's 0 or 1. But that's all right. That's all right. So, so this means, like I said, I'm trying to keep it a little bit easier to perceive here. So I went ahead and counted in binary um, from 0 to 15. So 0 to 15 in binary to represent the 4 bits that are going to be the fractional part. The whole number part, I just put a bunch of red X's, X, 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 X. It's going to be a 0, it's going to be a 1, depends if it's a whole number or not. So, it depends if it's greater than 1 or less than 1. So, like I said, X, X, X. Right now, it doesn't matter in this discussion. It's the fractional part that's always confusing. And so, let's talk about the fractional part. So we're going to have 4 bits fractional. And so it can be 0 to 15. So therefore, what this means is that we're going to, if we have, let's say 1.5, okay, the red X will now be a 1. Okay, so now the 0.5 is going to be halfway. We're halfway here. And what's halfway? An 8. So it'll be a 1 and then an 8, which would be 1, 0, 0, 0. So this is going to be a 1.5 in fractional part. Oh, sorry about the reflection here. 1 whole number part and then a 1, 0, 0, 0 is the fractional part that is the number 8. So the whole representation of 1.5 in a 1.4 format would be a 11000. Okay, because we're halfway there. We're just going to cut this in half essentially. We're taking a fraction of all the possible values. So that's pretty much what we're doing. And so now mathematically, you guys are going to be needing to do um, a microcontroller to do this, or you need to calculate it out exactly what the value is, because obviously with only 16 values, it's fairly easy to sort of figure it out. Um, so what are we going to do mathematically? Well, how many different possibilities are there where there are 16 different values, right? And so how did we get that number? Well, how many bits are there? There are 4 bits we're using for the fractional part. So we're going to say 2 to the 4th, it's going to equal 16. So we have 16 total values. And now if we're going to take the fractional part, the 0.5, that's that fractional part, or in this case, it was 1/2, we're going to multiply it. So we're going to take 16 times 1/2. And that'll be 1 times 16, and 16 divided by 2, do a proper equal sign, and it gives us an 8. So see, earlier I had said it's going to be a 1, 1, 0, 0, 0, because whole number 1, and then the fractional part was the 8. And you see, it works. 16 divided by 2, or times 0.5, 16 times 0.5 will give us 8. So you can take just the decimal part and multiply it by the total number of possible values. That's as simple as that. And in this case, there's 4 bits, so it's 2 to the 4. And so we get 16 total values. Um, Seems simple enough, right? And there's obviously going to be round off errors. So let's say if because we only have 16 bits worth of resolution. So, okay, that's still 16. So if we're going to say, well, what is 0.212? Well, okay. So 16 times 0.212. Yeah, I'm not going to try to figure out the fraction. It's going to be, an irrational fraction. So we'll stick with the decimal. So 16 times 0.212 will give us 3.392. 3.392. So obviously, we have to throw away this fractional part because we can't show a fraction within a fraction within a fraction. We can't do it. So we have the 3. So this will be in a 0.212 in a 1.0 format would be a 0 for the whole number portion and then a 3. So 0, 0, 1, 1. That will be 0.212 because a 3 is 0, 0, 1, 1. And obviously, the real answer is a little bit bigger than 3, but it's less than 4. And so this is quantization error if you're into digital theory here, because we only quantizing to 16. We only have 16 values to show, and if it's in between, it's in between, and we round it down as we should. You could round up if it ended up being 3.7 something. You can round up. That'll be a little bit less quantization error, um, but you get the idea. Now, if if you want better quantization error, you want less quantization error or better accuracy, you're going to go for more bits, right? And that's how you do it in digital audio. You have 10 bits, it's not 8 bits is not as good as 10, 16 bits, you get a little less quantization noise or quantization error, and 24 bits is better. And so you end up with pretty big numbers. Now, before I get to the big numbers, you're some of you might still be saying, I don't really get this. Now, I guarantee you that well, not every day, at least once a week, uh, you you do this automatically, and you're not aware that you're doing this. Uh, how do you ask? Well, most of us go to the store and buy things like food. Um, and okay, I'm going to go to the fish market and I'm going to get, a bunch of, cod is pretty good here in New England. So I'm going to buy some nice fresh cod or fresh haddock. And it's just me for dinner. So I'm going to want about a pound and a half. Okay, so I'm going to say, hey, I want a pound and a half. Well, how is that in weight? It's 1 pound, 1 pound, and what? 8 ounces? How many ounces are in a pound? 16. You mean like 4 bits? Like 16? So half a pound is 8 ounces? Yeah. You see, it's not as hard. You do this every day. You use this all the time. So now what about 1 1/3 pound? Well, it's going to be about 4 ounces. 3 or 4 ounces, 0.333. We do it all the time. We do it with weights and packagings. Again, it's a 5 pound, 12 ounce box that we need to ship out, and so it's 12 ounces. It's 2/3 of a, 3/4 of a pound. It's not. It's less than 1 pound, greater than the other. And the other interesting concept to see about this, you're never, well, I don't want to say never. You shouldn't say, well, it's 1 pound and 16 ounces. I mean, it's not like you're totally wrong. 16 ounces is no, you're going to say it's 2 pounds and 0 ounces, aren't you? Because there's 16 ounces in a pound. So you're going to go from 0 to 15. You're going to go from 0 to 15. The one you never reach that value. So you can only get up to 15. You can't quite get to 1. I mean, yes, when I can say, oh, 16 ounces is actually another pound, but no, we added another bit. We went up higher on the whole number portion. But as far as the fractional portion, if there are 16 possible values, you're going to go from 0 to 15. You're never going to reach actually 16. And this happens all the time in the digital world here in the fractional parts. You on the auxiliary ADCs, on the Sigma DSPs, it it goes it never reaches 1. It goes from 0 to 0.9998. I can't remember the exact number. It never quite reaches 1. Why? Because it's only a 10-bit number. It's going to be 1, 1, 1, 1, 1, 1, 1, 1, 10 bits of ones. Because it'll never be able to reach the one more bit because it only has 10 bits and it's all fractional. There's no whole number portion. And so it'll only go up to 111. It's like these 4 bits. It would only go up to 111, and that's the highest it's going to be. Not quite that fifth bit. Not quite a 1, which is handy. It's handy to know this on the aux ADCs. They'll never reach 1. So when you're multiplying and using tables and things like that, lookup tables, it's always good to know that it'll never reach 1. Um, so it can be very handy in doing those calculations. So that's another important concept to understand, that we'll never really, really reach 1. Um, so in large numbers, in the digital world, when we have a 24-bit audio sample, which is so much of the time we're in 24-bit audio stuff, uh, full scale is going to be, well, we have 24 bits. However, the MSB is a sign bit. And if you remember when I talked, if you look at my other video and two's complement number, so there's a two's complement video you can look up. We're going to start in the middle. Um, we we'll have 0 be in the middle, and then we'll go up to 15. And well, in this case, yeah, we'll go up to 15, but then negative will go 1, 1, 1. So we'll go up to 0. Well, actually, go up to 7. 0, 0, 1. Sorry. 0, 1, 0, 2, 3, 4, 5, 6, and then a 6, and then a 7. So 7, 6, 0, 1, 2, bop, 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 6, 7. So the highest positive we'll go is a 7, and then we'll start going negative. So this is a -1, -2 will be a 1, 1, 1, 0, etc., until we get a 1, 0, 0, 0, and that's a -1. We can actually reach -1 on the negative side. On the positive side, we can never reach +1, but we can do it on the negative side. So, anyways, so with a 2's complement number, we have a whole number portion, which is really the sign bit. So for a 24-bit audio sample, it's a 1.23 number. That's it. We're going to have two, uh, 2 to the 20. See, here with the 4 bits, I said we had 2 to the 4 for total possible values, and that was 16. So in this case, with a 1.23, we got 2 to the 23 as the total possible values. And so if we're going to now say, well, what is 1.5? Then we're going to take 2 to the 23 and we're going to multiply that by 0.5, and that'll give us the hex value. Okay, I'm going to interject a little bit in here. Now, if you have, we had 2 to this, 2 to the 2 to the 4, which is 16. So 16 total values times, and remember we were doing I was doing 1.5 a minute ago. So the fractional part, so 16 times the 0.5 gives us the 8, and that's the 8 we used for the value. So the formula for calculating is going to be 2 to the 4 times, times the fraction will give us the fractional part, which is, that's the fraction, and that's the 8 is the fractional part for the number format. So now, if we need to do it the other way around, because we don't, what if we don't know what this is? So, but we have the value. We look in Sigma Studio and we look at it and we see the value that's in the parameters, and so we need to calculate it the other way around. So how do we find out what the actual fraction was? Well, if we have this equation and we want to solve for 0.5, then we're going to divide both sides by 16. So 0.5 will equal 8 over 16, which equal 1 over 2, which is equal to 0.5. So the formula of the fraction, I'll just do the fraction, is going to be the actual value you have divided by 2 to the 4th, or the full number of possible values. So you're gonna grab the fractional value out of the data. It'll be an FFF whatever number, FC012 whatever, and you're gonna divide that by 2 to the 23 or whatever value you need for the fractional part. In this case, it was 2 to the 4. And that'll give us whether it's 0.5 or 0.2, etc. Obviously, there's round off, there's truncation errors because there's, it won't, I got a nice number here. I used 0.5, so it comes back exactly. If I didn't use 0.5, we wouldn't get 0.5 back exactly. We would get rounded to the nearest whole number. So. Anyways, that was a little side note I wanted to add back to my earlier discussion. And that's how you do it with your microcontroller. You can take 2, and what I would do in your program, by the way, take 2 to the 23. Don't calculate it every time. That's quite a lot of work. Just store it as a constant and then use that constant, because you're constantly going to be using 2 to the 23, because it's a pretty big number. And that's going to be the total amount you could go positive or negative, for the fractional part. So 1.23 number is what we're using, and you can never quite reach 1. Remember that. You won't quite get to 1 with a 1.23 number when it's on a converter that is a 24-bit converter. You won't exactly reach a 1. Um, you come awful close. Um, and This also applies to converters too, but this really should probably be a different video in applying this to calculating levels with digital converters, A to Ds, D to As. But a lot of this very much applies. In the Sigma DSP cores, on the Sigma 100 and 200s, we have a 28-bit number in the core. And since we're taking in a 1.23 number, we're bringing that into a 28-bit core. So what we do is we keep the dot 23 as the dot 23. So we keep those 20, we transfer those 23 bits, and then we have the 1, and then we add the extra bits. So it ends up being a 5.23, which adds up to 28 bits. So we have 5 bits for the whole number portion. And that's it. So we have 5 bits for the whole number, and we have 23 bits for the fractional, which gives us pretty good resolution for a fractional number, right? Because that's a big number. But we have 5 bits. 5 bits. That means what? Considering that the top one is a sign bit. So you can't use the sign bit. That means we have 1, 2, 3, 4, 5 bits as the whole number portion. Where's my red marker? Oh, it fell on the floor. I want to show the whole number portion red here. So we have 5 bits for the whole number portion, but this is the sign bit. So we really only have 4 bits to show a number. Because again, we'll never, with the sign bit, we can't really use it as part of the number. It's just positive or negative. So the most we're going to have is 4 bits. So with 4 bits, 15. 15 is the highest we can get for a whole number. So in a 5.23 number, the whole number portion, the biggest you can ever use is a 15. And this is why when you go into the gain cells and you say, I want 25 bits of gain, 24 dB of gain. So you put in 24. I want to multiply by 24. So I put 24 in and it changes it to 15 because the biggest it's going to be able to show is a 15. Because 11111 this is a 15 in decimal. And so if you need to show more bits, then I've done tricks like multiplying by 10 or I'm dividing by 10, etc., to give me more bits. Okay, I need to add in here about the Sigma 300 cores. I had kind of overlooked this. In the Sigma 300 cores, uh, we'll take a 1.23 number. We're going to bring that in to the core. Now, the 30 core, the Sigma 300 and 350 core is a 32-bit, 32-bit core. And so what we do when we're bringing in this number, and we'll take the dot 23 and we will add a bit to the bottom. So we'll make this a dot 24. So we'll take the 23. Hold on, let me get this words out of here. We'll take those 23, we'll add a bit to the bottom and make it a dot 24. Then we'll take the whole number portion and we'll add 7 bits to the top to make this an 8.24, which add these two up, it's 32 bits. So we're using all of 32 bits. And that's how we get an 8.24. The 1.23, the 1 ends up being the first number of the whole number portion. So we have 8 bits here. 1, 2, 3, 4, 5, 6, 7, 8. Got 8 bits and then the dot and then of course the 24 bits here. So the first bit, of course, is the sign bit. So that doesn't help us in representing whole numbers at all, except for positive or negative, of course. But um, so it leaves us with 7 bits here, 7 bits, and 2 to the 7 is 128. But remember, we can't go all the way to 128 because just like we couldn't go to 16, we have 4 bits, so we couldn't go to 16. We can only go to 15, 1, 1, 1, 1. So we can only go, the biggest we can go are these 7 ones, which is 127. So this is why in the Sigma 300 core, you can multiply by 127. You can go as high as 127 with a whole number, which is pretty cool. Um, on the negative side, we can go down to 128, but on 127 on the top. So yeah, that's a big improvement over the 1701 or the 1761 cores, the Sigma 100 and the Sigma 200 cores that are both 28 bits. It's a 5.23 number, um, and we can only go up to a 15. Well, here we can go up to 127, much more useful. We have a ton more headroom. Uh, but I'll talk about headroom in a different video. And then we have one extra bit in the bottom too, which is handy. And so when you're coming out of the core, then that's where if there's any ones here or any zeros, I'll go over that in a minute here. So yeah, I just needed to add that little bit. Thank you. Uh, don't forget to like the video and hit subscribe. Thank you. Bye.